We are going to solve problem 3.57 in Introduction to E and M by David Griffiths. We are asked to find the speed, angular momentum, total energy of the particle executing a circular motion in the field of an electric dipole, and also characterize the plane of the orbit. First, notice that the field of a dipole looks like this. We need a circular orbit where the field is always pointing toward its center. Obviously, this is the only place. Therefore, we look for the field at this point. Here is a simple plot of the field. We can take alpha to be pi minus theta, so both cosines and sines are positive. The field on the z direction must cancel out, leaving only the radial component. So we have 2 times cosine alpha equals to sine alpha times sine alpha, and we can solve for cosine alpha and sine alpha. We can also characterize the plane now. We are given the radius of the motion s, so we have z equals to minus s cotangent alpha, or simply this equation. Now, let's move on to the speed. We can use the fact that the electric force serves as the centripetal force to solve for the speed, but first we must find the field. Let En be the field at this point. We can go back to this figure to have a clearer look. Obviously, the total field is the sum of the s component of these two vectors, which is 2 times cosine alpha times sine alpha, plus sine alpha times cosine alpha. We simplify this expression, using the fact that s is the distance to the center of the orbit, which is r sine alpha. This is the simplified result. Now the formula of the centripetal force is mv square over s, which is also q times En, and we can solve for the speed. The angular momentum is msv, and the result is here. The total energy is the sum of the kinetic energy and the potential energy, so it's 1/2 mv square plus qv, plugging in the potential of a dipole and cosine theta we found previously, and the result is 0.